wide variety of processes going on with them. Volcanic activity, got impact craters, got big cliffs to leap off, so there's certainly a lot to do. And it's the key to all this is not just to look at pretty pictures, but is to impart the idea that examining these and studying all these various features give you a lot of clues and information to what's going on both inside the planet now, in the past, but also what's happened to the planet's surface in the past, and also, as you'll find out later on, what actually happened to the solar system in the past, and it's all on the surface of planets. So, to that effect, it's really three key processes that impact on planetary surfaces. Weathering through wind, water and chemical. We covered a bit of that with our talk on Mars, so I'm not going to be going back over that again, but we're going to split the talk into part one, which will be tonight on tectonic and volcanic forces, and then part two will probably be in February, because next month is the end of year quiz, and we've got something else special on as well, so we'll probably then pick it up with impact cratering in February, before we move on with the 2019-2020 series, which is going to be all on stars. Right, so let's move on. Part one, tectonic and volcanic forces. So, as we've mentioned, plays a huge part in these two forces. Probably these are the two biggest and most obvious forces affecting the surface of planets. And certainly, as we mentioned, it's a good way to probe inside the Earth is by studying these volcanic activities and earthquakes and so on. So, I've just given you a bit of a roadmap on how we're going to organise tonight's talk. The talk's going to be framed by an introduction and a summary, and then there'll be three main parts. I've split it into crustal faults that occur on other bodies in the solar system, otherwise not the Earth. Then we're going to look at the Earth as a special case of its plate tectonics, and then we'll look at some of the effects that volcanoes have on the surfaces of terrestrial planets. And that's going to take about 30-35 minutes, and I figure that's enough for me to talk, and certainly enough for you to listen to me. So, and then I've got a nice little 30-minute, I don't know if you've, people who, sort of last year and the year before, I had a whole collection of these little 30-minute lecture movies where it's a professor from the States is going to be talking on Journey to the Centre of Planets, bringing all this together, expanding a lot of these ideas, and giving you information about what goes on inside of planets. Welcome, you just arrived. Would you like some handouts? You've got handouts? Oh, good on you. All good. We're all pretty relaxed here. That's great. So, the introduction. Certainly when you start talking about volcanism and tectonic forces, you seem to get four fundamental questions from people. Let's just get rid of that cursor for a while. The first one is, what is tectonics and volcanic plate? What does it entail? Well, essentially what it means is this tiny little wee thin crust that's around the planet that we've got Earth here is modelling up. It refers to significant deformations and changes in that little wee thin crust because of dynamic forces that are occurring on in the mantle just below it. And that's what we mean by tectonic and volcanic processes. The next thing is people want to know is what's going on inside the Earth, inside of planets. Well, the bottom line is it's hot in there. It's really, really hot, and that heat is trying to get out the best way it can. And it does that through one of the most efficient ways of offloading heat is through the process of convection, and that's just like your water boiling on your jug and your pot and stove and stuff. That is a very, very effective way. And it's the same, it's just the heat boils up all that mantle, and the mantle just turns around in convection cells, and it influences the crust above it. So the bottom line is it's heat inside trying to get out, is what's going on. The next question you might say, well, where does all this heat come from? It comes from two main sources. First of all, it's called heat of formation. When the planets first formed, the solar system was a pretty violent place. There was smashing and collision going on everywhere. And as you will learn when we talk about impact cratering in February, when bodies collide and impact with one another, they contain a lot of energy. You're talking huge amounts, and suddenly you've got just multiple collisions going on that becomes molten and very, very hot very, very quickly. The second one is radioactive elements. And that material that formed around the sun, that formed the protoplanetary disk that then the planets formed into, that was full of radioactive elements, which then get incorporated in the planets. They sit inside, they just radioactively decay, and they emit heat when they do that. The three big ones inside the Earth are uranium, thorium, and potassium, and other biggies. So those are your two main reasons. There's a lot of heat trapped inside the Earth, desperately trying to get out, which is suddenly driving all these crustal deformations, which we call tectonic and volcanic forces. So the next thing is not to look, are there different types? Yes, there are different types of tectonics. Main one is compression and extension. In other words, just going this way, it can be compressed or go outwards, and it can go horizontally or it can go vertically. And then, as we mentioned, the special case of plate tectonics on Earth. And I personally find it's easier to break it up and have a discussion on all the non-earthly solid bodies of the solar system, and then go to talk about planet Earth as a separate special identity. So, let's talk about crustal faults on other bodies. Who knows, it's going to be interactive too. I've used some terms here. You might think, God, these are fancy science terms. Why use this rubbish? You always need to learn when you do a presentation to actually put things in plain English. And I thought, no. I said, I better not say that. Let's put the terms in, because it's an opportunity for us to talk about terms, what they mean, and when you see them next time in another presentation or a book, you know what they are. So who can tell me what's a graben? No, it's a sunken bit of ground. It's a ground that just sinks down. They call it a graben. So the clever planetologist. Scarp. Who can say what a scarp is? Yeah, what's that? Yeah, a cliff essentially. Yeah, so it's a cliff. So in other words, vertical, depressed bits. And do you know what the opposite to a graben is? It's called a horse. That's where a bit of land goes up. And often you will get a bit of land that goes up, and you get a little bit of land down in the middle that sinks down. So you've got your horse on either side and your graben down in the middle. Funny words, I know, but I thought, nah, damn it, I'll put them in. It's an opportunity for us to talk about them and just get familiar with some of the terminology that you'll read when you pick up a book. And of course, horizontal faults. Okay, so let's move on. So you can see here some graben or depressed bits, little canals running through here, and see all these little craters? So these sunken regions of crust. Who can tell me where this is? Because it's pretty unique to one planet. What planet are we looking at here with these gradens, these depressed bits of canals and some of these craters? They're not actually impact craters, they're called ghost craters. They're just sunken bits of the ground. Any takers? Don't be shy.
Mars.
No.
Mercury.
Yes, Mercury, yeah. It's unique to Mercury. It is there. And what does that tell you? When something shrinks, it means it's cooling and it's contracting. So that's part of the key evidence you might read in a book. Mercury's cooled off and it's contracted. And you think, how do they know that? That's how they know that, and that's why people study surface features of planets. And they're called graben. These are called little ghost craters here, where they're just sunken bits of ground. And that's because Mercury has contracted and shrunk. As it's big white, it's relatively small. Just getting the hang of this. It goes that way, doesn't it? We're in business. Okay, and there's some nice close-up ones of those ghost craters. Okay, now this is a big cliff or a scarp. Who can tell me whereabouts in the solar system is this huge big, it's the largest or the highest cliff in the solar system? Yeah, Tony's the closest, one of the other moons.
It's one of the other moons, I can't remember its name. But,
Uranus's icy moon, Miranda. Miranda. Did someone say it? Did they? Yeah, that's Miranda. And that's the tallest cliff. They don't know really what caused that. That's it sitting right there. They think it could be so because it's an icy moon. Ice, of course, contracts quite happily. There was some tectonic forces. some people say, look, it even could be an impact. We don't really know, but it's certainly, that's amazing. So that's the 20 kilometres high, that cliff. So if you fell off it because of the low gravity, it would take you 12 minutes to fall from the top to the bottom. You'd be in 12 minutes to make all those last minute phone calls. Before you hit the ground 200 k's an hour. A little bit of trivia there.
I can see that being
Okay, moving on to crustal faults. So you can see a huge big fault line down through here. It's a large canyon. We've mentioned this a couple of times throughout the year. Where is this? Mars. Yeah, what's its name? Yeah, yep, absolutely. Now this, its dimensions, it's 4,000 kilometres long from there to there. That's almost the width of the United States. It's 20 kilometres across and 7, that's most impressive to me, it's 7 kilometres deep. That makes the Grand Canyon just a walk in the park. And you might say, what on earth is that? What does that tell you about? And the clue to what's formed that, here it is here, this is topographical map, where red is high and blue is the low northern lowlands of Mars. And you can see it stretched right across Mars, right across the planet. It's a pretty obvious feature. But over here, you've got this huge big volcanic plateau called the Tharsis Rise. And that's huge heights, and these got 3 big volcanoes on it as well. And the general theory, consensus, is that as that volcanic rise all started lifting up with the pressure of the hot magma underneath, it cracked the crust beside it, and it makes sense, it just gave way. So that's probably a crack from there, and there is another picture of it there. That's another topographical picture, just to take in the depth of it. Once again, blue is shallow, red is high. And here's your Tharsis bulge, just a part of it over here. So you can just imagine that lifting up and all the crust near it just cracking, essentially faulting. So that's just a quick tour of the rest of the interesting features around the solar system, some interesting little sort of tectonic points. We move then on to plate tectonics on Earth, mentioning briefly the reason we look at Earth. Mars and Venus do have tectonic plates, but they're just what they call one-plate planets. Lara, you were the one who got that. We didn't talk on Mars. You said that's a one-plate planet. So we're going to look at Earth. It has multiple plates, and these multiple plates are what give us our interesting things of mountain ranges, oceanic ridges and trenches, subduction zones with volcanic ridges, and chains of volcanoes. So let's find out how it all happens. And here's our numerous plates, how they're all sort of mapped out over the Earth. You can see going right through here, the boundary going through New Zealand. That's why we get more than our fair share of earthquakes here. And it's the movements of these plates. And that's the key to all of this. It's probably the 2 big keys to a lot of this tonight is that the Earth is all about tectonic plates. It's the movements of plates, in particular it's the boundaries, the movements and the boundaries of these plates that cause all the action. And that's it. Yeah, plate boundaries are the site of all the action. And there's 2 different types of boundaries. There's divergent, and that's where you get 2 plates and they're pulling apart. Or you get the opposite, convergent, where 2 plates pull together. Or you what are called transform boundaries, and that's where plates move side on with one another like that. And those are your 3 combinations. First of all, we get 2 plates converging. Typically that will occur in the middle of the ocean, and you get these oceanic trenches and ridges that occur bang in the middle of the ocean. That was all theory for some time, until they actually went out there looking for them and they found them, and that was one of the key evidence for tectonic plates. And this really, there's a couple of interesting points of discussion here. One is the reason I put these diverging plates as my first slide, talking about how boundaries meet, is because this is the principle what drives the whole thing. You've got fresh mantle, hot mantle coming up and pushing plates apart. It's like elbowing your way into the room. This is the key driver behind the whole process, is these divergent plates, mid-oceanic trenches and ridges, pushes it apart and drives everything else. The second point is it gives important information on what's going on not only now in the Earth, but also what's happened in the past. How many times do you pick up an article somewhere in the paper and it says that possibly the magnetic field lines around the Earth are changing? And they haven't changed for 200,000 years, so they're well overdue. You think, how on earth do they know that? They know it because these rocks from the mantle come up, push out here, and these are all time-made. And they just sample the rocks, pull them up, take them back to the laboratory, then they document exactly where part of the ocean they came from. They do radiometric dating, so they date the rocks. They know, well, this rock here is a million years old, or it most likely be something like here. This is 5 million, this is 4 million, 3 million, 2 million, so on, with this being the freshest. But the other thing they do is then they look at the orientation of all the iron filaments within the rock and see how they're aligned. So they can tell when and how the magnetic field lines in the Earth were all aligned from these rocks that come up. So it's just laying out beautiful stratifications in a nice timely fashion of the Earth's history. So that's sort of the main point of discussion there. So moving on to converging. So that was two plates being pushed apart. How about when plates come together? There's two types, one when they start folding or when they start subducting. So the folding and converging boundaries, of course, when you get land, starts getting heaped up, and it's no surprise that's what gives you mountain ranges. And who knows, no prizes there, what's the mountain range is that? Yeah, Himalayas, yeah. It's a relatively young mountain range. That's why it's not so high, because erosion hasn't got the better of it yet. And there's Mount Everest up there, and that's why it's the most high. So why is that whole mountain range there? It's because the Asian plate is jamming into the Indian plate. Both of them are heading in one direction, sort of heading towards one another and all starting to fold up. And that's what's causing the Himalayan mountains. And it means it's a reasonable, geologically speaking, it's a reasonably recent event, this whole process, and hence that's why it's the highest peaks in the world. The other one, when two plates to meet, is what's called subduction. And the idea here is this, a few talking points here too of discussion. One is you've got two types of crust. You've got oceanic crust plates, which are very thin but really heavy, and you've got oceanic plates which are very thick but are very relatively light or less dense than the relatively heavy, thin oceanic plates. So when these two guys meet, what happens is the heavier, thin oceanic plate slides down and gets driven down underneath the continental, the higher, thicker, lighter continental plates. It's just a natural process. Gravity just pushes it down. And of course, it's been driven by two things at this point. You've got two drivers and one assistant. You've got one driver with the diverging, the fresh mantle coming out that we spoke about. That's shoving things this way. As soon as that subducting process gets underway, you've got gravity pulling on it too, just pulling the rocks down. So those are your two drivers here. And your assistant, which it plays a very important role, which gets overlooked, is all Earth's rocks are full of water, and the water acts as a wonderful lubricant. Some planetary scientists will even argue if it wasn't for water, this process would not have the strength to go ahead and do. The other point of discussion is here, so when this crust it doesn't just slip quietly down here, as you can imagine, you've got a lot of force going on here. You've got this entire range of mountains all sitting on top. You've got this being shoved down. It doesn't just simply slip and slide on down. There's a lot of wrenching and grinding and graunching. It's been shoved down really hard. So a lot of friction and heat is generated here, thousands of degrees. So naturally all the stuff that's getting subducted back down starts to melt and starts to push all this land up, and that's when you get whole ridges of volcanoes. And this classic example is from New Zealand. We've got a nice little rim of volcanoes, White Island and so on, all the Ruapehu down to the South Island and stuff. So we've got tectonic plates there that are causing this exact process. So that's subduction. We'll also get an oceanic trench just along where it is diving down. this one here is the third type of boundary, which is where tectonic plates aren't coming together or they aren't being pushed apart, they're just sliding back towards one another. And of course we all know what that gives rise to: earthquakes. And with an earthquake, it doesn't just sort of just go slide, 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 slide. Of course, you know, they're fairly sticky. The plates are reasonably sticky and pushed up together. So what they do is they hold the stress there, and all of a sudden they'll just give, and suddenly a quick jerk. And that quick jerk just gives a quick, sudden bolt of energy right through the surface of the earth, right through the crust. And that's what causes our earthquakes. And where is this famous fault line? Yeah, San Andreas, yep, in California. Look, it's pretty impressive, isn't it? Yeah, when you see a photograph like that. Here it is running up through there, through California. So when that has its day, half of California will be in the sea. You'll have some San Bernardino will be seaside. So what happens when you get these big shocks going through? There's a series of waves that go through the earth. There's surface waves, there's what's called primary and secondary waves, and they all have different characteristics, which the movie I put on at the end of this talk goes into a little bit more depth. But some of them are shear type of movements, some are compression type of movements. Of course, like all different types of waves go through different materials at different velocities and different strengths. So of course, all you do is monitor around the earthquake occurs here. You've got little stations dotted all around the earth. They measure the time that the earthquake happened here, measure the arrival time off the different angles at the different waves and what angle they came in, because you get refraction. Suddenly waves will change their direction as they hit a medium of different density. So the computers crunch all those numbers together, and that is the prime way they work out how the Earth is what it is, all its different layers. Because you must wonder, how do they know it's a core? How do they know it's a liquid core? How do they know the different layers of the mantle and how deep? It's earthquake cosmology is how we tell all that. It's a whole science in itself. So that's a perfect example how crustal events, because of moving tectonic plates, tell us exactly what's going on inside the Earth. Now, just like you get earthquakes, you get moonquakes. The Apollo astronauts left seismic equipment on the moon, which they kept going for many years, which we're going to have a look at the movie shortly and talk about moonquakes and Marsquakes.
Mars.
So, let's see if I can work this apple here.
Over at SOP.
Okay.
Over at SciShow, we've talked about the science of earthquakes, how the shifting, sliding, pulling, and pushing of Earth's tectonic plates causes the seismic activity that we all know and love and kind of fear. And what about our celestial neighbors? Are there earthquakes on worlds that aren't Earth? Well, in the 1970s, Apollo astronauts placed seismometers on the moon to see what it was up to. And until the last of them was switched off in 1977, these instruments recorded more than 12,000 seismic events of varying degrees, including one quake with a magnitude of 5.5. And Mars, meanwhile, has been found to have a system of faults or fissures in the crust, and possibly volcanic activity. But moonquakes and Marsquakes are different than earthquakes. What makes moonquakes so interesting isn't so much their magnitude, but their persistence. Most quakes on Earth tend to dissipate after a minute or so, because water interacting with the rock below the surface acts like a kind of sponge to tamp down the vibrations. But not so on the moon, which is cooler, drier, and more rigid. Its surface isn't pieced together from tectonic plates like Earth's is. Instead, it's been described as being like a tuning fork. Those old Apollo instruments have recorded shallow moonquakes lasting more than 10 minutes. Some of these are likely vibrations caused by meteorite impacts. Others are probably thermal quakes, caused by the difference in temperature between the lunar day and night. each of which lasts about 2 weeks. When sunlight first strikes the moon's surface, the expansion of that frozen crust can cause seismic activity. But the most common moonquakes appear to be related to the tidal stresses between the Earth and the moon. The mechanisms behind them aren't really well understood, but these quakes happen pretty regularly and seem to be the result of internal stress caused by the moon's gravitational interaction with Earth. These quakes are low magnitude, but occur at great depths, as much as 700 kilometers below the lunar surface. Then there's a whole category of shallow moonquakes that originate between 20 and 30 kilometers below the surface that still have scientists baffled. Yep, we're still analyzing data from 1977, trying to figure out the origin of all the moon's quakes. Scientists know even less about Mars quakes, in large part because we don't have the trove of data that we do from the moon. In fact, only the Viking landers, which touched down on Mars in the mid-1970s, had seismometers on board. And the only quakes they detected came from vibrations as the spacecraft landed. But recent photographs by NASA's Mars Reconnaissance Orbiter have revealed intriguing new evidence of Mars quakes and volcanic activity. The orbiter revealed a pair of long gashes in the Martian surface that appear to have formed following eruptions of a giant volcano known as Elysium Mons. The mountain probably hasn't blown its top in millions or maybe even billions of years. But photographs suggest that there's still movement below the surface. The key evidence is fresh boulder tracks, traces left in the Martian soil by the movement of huge boulders, which scientists believe could only have been caused by seismic activity. A 2012 analysis of the tracks from boulders, ranging in size from 2 to 20 meters, found that the number and size of the tracks decreased over a radius of 100 kilometers from the faults around Elysium Mons. Scientists estimate that a relatively recent Mars quake with at least a 7.0 magnitude was responsible for jarring these boulders loose. So hey, Los Angeles and Tokyo and Mexico City, I guess it's good to know we're not alone. Right? Thanks for joining me for SciShow Space. If you want to learn how you can help us keep exploring the universe together, just go to subbable.com/SciShow. And don't forget to go to youtube.com/SciShowSpace and subscribe.
Don't forget to subscribe, guys.
SciShow.
Okay, so we've talked about this. Quite an interesting little chat. Talks about quick, but it was good. Hotspot volcanoes. We've talked about what happens when tectonic plates move around. Also, you get another concept of volcanoes that can occur not at the plate boundary. Typically, if they're going to occur over a crust, they're just a hot spot in the mantle that comes up and bursts through the crust like a pimple, really. Now, if it was going to be an oceanic crust or a continental crust, what's it going to be? What's thinner? Oceanic crust, yes. It's typically over the oceanic crust is a lot thinner, remember? So it's typically, it'll burst up, a bit of hot magma will burst up through a hole there in the thin oceanic crust, and that creates a volcano called a hotspot volcano. Now that's a hotspot volcano, the largest and highest in the solar system. Who can tell me what that is?
Olympus Mons.
Yeah, Olympus Mons, absolutely, in Mars. That is 24 kilometres high. So that's 3 times higher than Mount Everest, Olympus Mons. And the reason it's got so high, lower gravity, so it can go up higher, but also Mars, one plate planet, instead of all these thin plates moving around, it's just one big solid mother of a planet. It can hold up something like that without it starting to sink down into the mantle. Here's another hotspot volcano somewhere else in the solar system. Where is this? That's outer moon. Io, just the largest moon of Jupiter. The most volcanic place in the solar system is Io, the closest moon to Jupiter. And it's a combination. You might say, well, what's driving the heat? It's pretty cold out there, isn't it? Colder than my beer fridge. The reason it's got the heat, it's a complex, it's multiple tidal forces between Jupiter pulling it in, and it's getting tugged the other way by its fellow moons going around in orbit. So it's called tidal force, and it creates a lot of tension and heat inside Io, and you get these little volcanic eruptions. There's some other stuff going out there. Where is this? This is obviously not a photograph, this one. So this is Enceladus, one of the icy moons of Saturn. And they see all these water geysers coming up, just like as in this diagram shows. And what that is evidence that there's global subsurface oceans of water behind probably a handful of these ice moons, Enceladus, Europa, around Jupiter, possibly some others. So, which is interesting, of course, looking for life out there. Is there life out in these moons? Quite possibly. But how do they know this? They know it from all this activity that's going on here. So once again, another good indicator. Looking out for volcanic and tectonic activity gives you a window into what's going inside a planetary body. So here on Earth, here's a chain of hotspot volcanoes. And the reason you've got this chain is because before, remember we just had a hotspot that came up and just sat there like for Olympus Mons, just started getting bigger and bigger. But on Earth, those oceanic plates are moving. So they're just constantly moving along. So as you get a hotspot volcano that comes up, the plate moves along a little bit, so you get another one, and so on. You get these chains of volcanic islands. So that's a very famous one. Where is here? I've been quietly covering all the titles up. Whereabouts is this? Hawaii, yeah. So I once read in the book, Hawaii is a country still under construction. Quite a good way to put that. So indeed, it's the high, and there's the plate motions moving on there. So your hotspot must be sitting around here somewhere, and the plate's just quietly moving along.
Just the south, Chris, is the New Island that hasn't come broken surface yet.
Right, okay.
The New Island forming hasn't broken surface yet.
Yep. So you run around their boats waiting to claim it. Trump Island. You need Trump Island.
Oh.
I like it. Trump Island.
Hawaii actually does have special laws relating to new land.
Oh, okay.
Like the recent eruption basically filled in a bay. So there's, in the past, there things like that happen.
Yeah.
Puke over Hawaii.
Yeah.
Owns it and that
Yeah.
kind of thing.
Interesting. Thanks. Yep. So we're going to move that naturally. These are the effects of volcanism, lava flows. We're going to talk about collapsed lava tubes and resurfacing. So we've been talking about Hawaii. I don't know where that is, but I wouldn't be surprised if it is Hawaii. You can see these lava flows across the land, destroys houses, property, farms, and you can't stop the lava flows. But lava not only flows on the surface, it also flows under the surface in what's called lava tubes. And that's an old lava tube. It's obviously the lava's just moved on from there, and you find these dotted around the Earth now as lava tubes. And it makes sense that if you get lava tubes around the solar system, they can collapse with time. And here is a collapsed lava tube. Who can tell me the name of this? They call them rill, by the way. When you're on the moon, you call a collapsed lava tube a rill. So you can tell me what Apollo mission this was from and the name of the rill? Yeah, exactly. Apollo 15. Yeah, Hadley rill. Yep. That's either. Is that Jim Irwin? It's Jim Irwin. He hasn't got his red bands on. So that's Jim Irwin there with his lunar rover. Now, interesting enough, I put some figures down here. Yeah, that slope doesn't look too bad. The depth of that is 380 metres, and the slope is 25 degrees. So you can see why they didn't want to get too close to that rill. They want to get close enough to get some samples and have a look at it, but probably more looking sort of on that direction. You would not want to get down there in an astronaut suit. You would probably not get back up again. I believe they had some sort of contingency of ropes and up, but at 380 metres, I don't think they would have been successful if one of them had fallen down there. That's a picture of it, sort of the Hadley Rill, just winding its way, sort of meandering, sort of magic lava flow from the highlands down here to the lowlands. That would have been a nice big tube of lava, but with time the lava tube has just collapsed. Goes for 130 kilometres, that rill, lava tube. So that's another feature of previous lava flows on the moon, of volcanic activity. Once again, you hear it again, you look at features today, they tell you what went on inside the moon many millions of years ago. Resurfacing occurs. This is, which planet is this? I tell you, almost totally resurfaced every few million years. It resurfaces itself. Venus, oh there it is. I hate making something easy. So yeah, that's Venus. Venus has got many volcanoes. And what volcanoes do is they resurface, so provide new surfaces, mow over old surfaces, and that's a radar image of what Venus probably looks like one of its highest volcanoes. It's just a lot of lava and stuff everywhere. So most of it's, I don't carry the figure in my head, but it's something like a few 100 million years old is the surface, relatively very young. So, just summing up, and then we'll time on for our little movie lecture. Tectonics and volcanism, we've learned it refers to crustal deformations, big deformations on the relatively tiny crust, from big movements and activity going on in the hot mantle, because it's hot in there and that heat's trying to get out. You have non-earth body things. We have dips or sunken patches, which people in their wisdom call graven. We have scarps, which is a fancy word for cliffs, and we have fault lines. Plate tectonics, we hear the key to it. Most of the action on Earth happens at the boundaries of these mobile tectonic plates. We take away one message today, that's it. We've got multiple mobile plates on Earth. You get boundaries that are pulling apart, which is new material coming up, just driving it. You get convergent boundaries, where they're all coming together, either to create a mountain range or subduction to create a ridge of volcanic series of volcanoes, or you get transform boundaries where you get your earthquakes, which create seismic waves for studying all the layers underneath the Earth. Hotspot volcanoes give you singular volcanoes on Mars and Venus, but it leads to a chain of volcanic islands on Earth. Well, that one wasn't too successful. I'd probably had a bit of tectonic plate movement. Okay, so key message to take home: tectonic and volcanic forces play a big part in shaping planetary surfaces and provide important clues to what's going on in the inside of that planetary body. Next time you hear a volcanic eruption or an earthquake, aha! That'll be you. You'll instantly know. I know what's going on there, and I know what information it's going to be telling them. So, most of all, what do you do? Have fun. Loads of fun. So that's just the brief 30-minute talk, and we'll move on to our little movie now. So it's Journey to the Centre of the Planet. It's going to recap some of that, plus expand on a few areas like earthquakes, and then it's going to just also fill you in a little bit more about the centre of the Earth. So let's see if I can operate this.
In 1864, Jules Verne published the book, A Journey to the Center of the Earth. In it, Professor Wiedenbrock leads his nephew and a hired guide down a volcano in Iceland, and they have many adventures where they sail across a subterranean ocean, they meet prehistoric creatures, they are hit by underground lightning, and they see a 12-foot-tall ape man, which they can't decide, is it ape man or man ape? And upon looking at that, I wondered, is that related to the fact that Darwin's On the Origin of Species was published 5 years earlier? But at the end of their adventures, they come to the surface in southern Italy by a steam vent of the volcano. Now, unfortunately, I don't think truth is stranger than fiction in this case. Because as we explore planetary interiors, we will see a subterranean ocean, but it will be made of magma, not water, so we couldn't really sail across it. Instead of lightning, we'll find magnetism, and we won't meet any prehistoric creatures, although there is a chance of life on Europa. Our trip to the interior will be based on bulk measures and external properties, because really, we have no chance of making in-situ measurements in the interior of any planet. We'll spend most of our time looking at Earth, where the data is strongest, and as we extrapolate to the other planets and bodies in the solar system, we'll have to be guided by mathematical models. And generally, when we look at the interior, we're really biased towards explaining the surface characteristics of the planets. So we'll begin where Verne begins his adventure on Earth's surface. Earth is a rocky planet, so let's take a look at the rocks and see what we can tell about the interior from just looking at the rocks. There are 3 main types of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are rocks that cooled from a molten state. Now, molten rock is called lava when it flows across the surface, and it's called magma when it's beneath the surface. Examples of igneous rocks include basalt and granite. Sedimentary rocks are rocks that have been deposited over time by wind, water, snow. For example, layers of sand can be compressed and you get sandstone. If the minerals precipitate out of the oceans and form on the ocean floor, you create limestone. It's interesting to note that the rocks at the top of Mount Everest are limestone. These are sedimentary rocks that formed at the bottom of the ocean and then were pushed up to form the highest mountain in the world. Metamorphic rocks are reprocessed rocks. If you subject igneous or sedimentary rocks to high pressures and temperatures, they will change their structure. Fine-grained igneous rocks become a different type of rock called schist. Limestone becomes marble. So when you're picking up your countertops and you have a choice between granite and marble countertops, here's the difference. Granite are igneous rocks. They've been molten once and then they solidified, while marble is a metamorphic rock that was processed as a sedimentary rock and then reprocessed to form marble. Probably that extra step in production means that marble costs a little bit extra. The implications from rocks for the interior of our planet are twofold. One, it shows that magma flows up from the interior. There must be some sort of magma ocean beneath our water oceans where the magma can rise up and form on igneous rocks. Second thing is that rocks must also flow down into the interior. Some of the crust is recycled because you're taking these igneous and sedimentary rocks and pushing them down into high temperatures and pressure to become the metamorphic rocks. Next, let's take a look at the oceans. Here is the standard picture of Earth's surface, and you can see that oceans cover 70% of the surface. There are 5 major ones: the Pacific, the Atlantic, the Indian, and down here in Antarctica there is the Southern Ocean that we don't talk about very much, and then at the northern latitudes we have the Arctic Ocean. The average depths of these oceans is about 13,000 to 16,000 feet, about the height of a really good mountain, but this is actual depth in the sea. The only one that's different is the Arctic Ocean, and it's a rather shallow ocean, goes only to about 4,000 feet deep. The deepest points of the ocean are shown in this topo map, where you can see trenches. Now, trenches tend to occur along the edges of continents. On the west coast of South America, you can see the Peru-Chile Trench. Along the west coast of North America, and stretching along past Alaska, is the Aleutian Trench. And then down past Japan, you have the Japanese Trench, and stretching out into the Pacific, you have the Mariana Trench. The depths of these trenches can reach to 36,000 feet. And that sounds really deep. But let's put it in perspective with respect to our planet. The average depth of the ocean is perhaps 5 kilometers, and the deepest is only 11 kilometers. Now, let's add in the mountains. 11 kilometers deep for the oceans, but add in the 9 kilometers of height for the mountains, you get about 20 kilometers of vertical relief. That's really only 0.3% of Earth's 6,400 kilometer radius. Now, I have here a globe, and some globes have vertical relief on them, where you can feel the mountain chains. If this globe had perfectly accurate vertical relief, going from the highest mountains to the deepest trenches, the thickness on a 12-inch globe, or a 6-inch radius, would be less than half a millimeter. You could rub your hand across it, and you still could not feel it. That's why most globes have really exaggerated vertical relief. The other feature of the seafloor are what we would call ridges. And in this topo map, we emphasize the ridges And you can see running down the center of the Atlantic Ocean, the Mid-Atlantic Ridge, and off the west coast of South America, we have East Pacific Rise, and from underneath Australia and India, we have the ridges in the East Indian Ocean. These are like undersea mountain ranges. They can reach up to 5,000 feet above the sea floor. And sometimes, especially in the Mid-Atlantic Ridge, they're cut by a rift valley. So you have the mountains, and then you have a rift valley cutting through. We interpret these ocean features under the guise of plate tectonics. In this image, we show you the plates of Earth. Earth's crust is divided into 8 large plates and a few smaller ones. We have the North American plate and the South American plate. We have the Eurasian plate, which stretches from Europe across Asia, the African plate. We have the Indo-Australian plate from India and Australia. And we have the Pacific plate down bottom. And then we have one plate that's just to the west of South America, which is called the Nazca plate. Those are the 8 major plates. There are also a host of minor plates. And the most easily recognizable one is the Arabian plate, that includes Saudi Arabia. Now, with these plates, you can see the boundaries of these plates fit with the ridges. And where these plates intersect are the regions of the trenches. The trenches are interpreted as regions of subduction, where one plate is going underneath another. The ridges are the creation of new plate material. When magma rises from the interior, pushes up these mountains, it solidifies and creates new plate material, and then the plates spread away from the ridges. This motion can be measured, and it's about a few centimeters per year. So if you think your flight from the US to Europe is long, it's only going to get longer as they actually are spreading apart from one another. The evidence for plate tectonics is incredibly strong, and they come from earthquakes and volcanoes. This is a map of where earthquakes have occurred over a 5-year period. You'll notice that it very strongly matches the seafloor topography that I just showed you. The number and strength of earthquakes are highest at plate boundaries. Now you'll also note that earthquakes can occur away from the plate boundaries. I take a look, and I live in the eastern United States, and I see there are a significant number of earthquakes that occur in the eastern United States. I'm told that a moderate earthquake in Boston could do more damage than a stronger one in San Francisco because the building codes do not anticipate earthquakes in the Northeast. The same is true for volcanoes. Here is a map of where volcanoes are found on our planet. They are not randomly distributed throughout our planet, but again, they match with the location of the trenches. The subduction of a plate underneath another plate leads to volcanic activity on the continental plate next to it. But once again, you'll notice that the correlation is not perfect. In particular, there are some volcanoes here in the middle of the Pacific plate. This is Hawaii. Why are there volcanoes in Hawaii? This is as far away from either side of the plate as you can possibly get. Well, let's take a look at the Hawaiian Islands. This is an overhead map of the Hawaiian Islands, and you can see the Big Island actually contains 2 very large volcanoes. The northern one is Mauna Kea, and that's dormant, and the southern one is Mauna Loa, and that's still active. The idea of how you make these volcanoes out in the middle of the Pacific plate is something called hotspot volcanism. There is a magma hotspot underneath the Pacific plate, and that magma pushes up through the Pacific plate and forms these volcanoes. As the plate moves across the hotspot, new islands in the chain grow. And you can see here from just the state of Hawaii that the islands sort of continue off to the northwest. If I take a wider view, you can see that it isn't just the islands that we see today, but there's considerably more islands that have been there previously. And if I look at a topo map, you can see that if I remove the water, then you can see that there is a huge long chain from Hawaii down here all the way up across the Pacific plate. There is at least 70 million years of hotspot volcanism in the Hawaiian island chain. And there's a new volcano that is forming just south of the Big Island, and they call it Loihi. And that eventually will become the new island in the Hawaiian chain. So that sort of inspires an intriguing question. What is the history of the plate motion? How have these plates been structured over history? Well, here are how the continents look today. And one thing you will notice is how the bulge of South America on the east coast would fit very neatly into the west coast of Africa. The Mid-Atlantic Ridge has separated these two continents over millions of years. If you look 60 million years ago, the continents were closer. And you can also note how far India is from the Eurasian plate. India, over the last 60 million years, has been a relative speed demon. It's been traveling at up to 15 centimeters per year. If we look back 120 million years ago, this was a time when South America and Africa were in contact. 180 million years ago, the Atlantic Ocean disappears. Matter of fact, we only have one much larger ocean, and we have a continent that's called Pangaea, one supercontinent composed of all the continents that we know today. Going further back to 240 million years, the land masses seem to migrate a little bit south. And going to 300 million years, it still remains mostly one continent as it continues to migrate south even further. At 360 million years ago, you can see that most of the land mass is below the equator. And when I look at this, I say, maybe that north-south dichotomy on Mars, where there's a significantly different topography in the south compared to the north, well, I guess it doesn't look so strange anymore. At 420 million years ago, it's no longer one continent. So the supercontinent of Pangaea was just a temporary state. North America has broken off. And I also think it's kind of fun to look at this and say, hey, look, Alaska, Greenland, and Russia, all of them straddle the equator. So we conclude that the continental plates have been drifting across an interior layer of a planet. I guess drifting is one word, but I think floating is a better word, because that will lead to the idea that's important to discuss next, and that's differentiation. We all know that oil and water don't mix. You put oil and water together, you shake it up, and then just let it sit. Eventually the water will drop to the bottom, and the oil will rise to the top. The water is more dense, and it sinks to the bottom. For planets, this idea is called differentiation. It's basically the simple gravitational separation of materials of different density. It requires, however, that the body must have been liquid at some point during its formation. So massive objects will have high temperature and pressure due to gravity. They naturally will become differentiated. What's more important for smaller bodies is the heat generated during formation. The cooling efficiency of a body is really a ratio of its surface area to its volume. And if these things are roughly spherical, the area is proportional to the radius squared, and the volume is proportional to the radius cubed. So the cooling efficiency goes up with size. Smaller objects will cool more efficiently. So you will expect large objects to be differentiated, but the smaller objects will be able to cool away their heat. They won't necessarily become liquid, and we might expect those to be undifferentiated. The tool that we'll use to explore the interior structure is seismology. And it's simply that earthquakes trigger seismic waves, and some of those seismic waves will pass along the Earth's surface. These are the ones you feel when you're involved in an earthquake. I did my graduate work at the University of California at Berkeley, and I experienced a number of these. Most of them were kind of fun, a little rolling of the room, but I was also there during the 7.2 Loma Prieta earthquake, and that one scared me a little. But the other seismic waves, the ones that are useful for exploring the interior, are the ones that are going to go downward and through the interior. And the speed of these waves is dependent on the density of the medium. They can also change direction or bounce when there are boundaries between different density mediums. This is like, refraction or reflection with light waves. When the wave hits the boundary, it can bounce back or it can change its direction. There are two types of waves that we will consider. First are called primary waves. These are what scientists call acoustic waves, and they propagate like sound waves. There's a compression and rarefaction as it moves along, just like the sound waves that you hear. The second type are called secondary waves, and these are shear waves. There is side-to-side motion. So this is like when you're wiggling a string or a bullwhip, back side to side, that's a wave passing this way. You will note that for a shear wave to work, if I push this piece of a body to the side, it needs to have some connection to the next piece of the body to pull it. Therefore, these shear waves can't propagate through a liquid. If I pull a little bit of liquid to the side, the next bit doesn't go side to side. So it's an important property is that the primary waves can pass through solids and liquids, but the shear waves can only pass through solids. The basic idea is that you know the epicenter of the quake. You measure the strength of the waves on the surface, determine the epicenter of the quake, and then around the globe at the seismic stations, you measure which waves arrive and when they arrive. If, for example, no secondary wave arrives, then you know there must be a liquid layer between that seismic station and the epicenter of the quake. The time of arrival will indicate the average density of the material that it passed through. Now, in this way, you can work to build up a model of the interior. It's not going to be a simple solution, simply because you do have these boundaries and you have reflections and refractions, but with enough data over many years, we've built up a very good model of the Earth's interior. Earth's interior structure is considered to be composed of several layers. Basically, the basic layers are crust, mantle, and core. The crust is roughly 60 kilometers thick, only about 1% of Earth's radius. It's composed of the low-density materials. And as you would expect, the low-density materials are the stuff that are going to float to the top of the differentiation process. It really is not very significant because it only contains 0.4% of Earth's mass. It is, however, very significant to us because it's where we live. One question we have is, why isn't there more crust? If you look at the materials that we think formed our Earth, we expect there should be 200 kilometers of crust. However, if you do the calculations, at around 60 kilometers, the pressure and temperature becomes so great that the materials of the crust undergo what's called a phase change. They become higher density materials, and the bottom of the crust peels off, or what they say delaminates, and then starts to sink. So the crust is kept at about 60 kilometers thick through this process. The mantle, the middle layer, is composed of rock and extends about halfway down to the center. It contains 2/3 of Earth's mass. There are 3 subregions in the mantle. You have the upper mantle, and that contains the asthenosphere. This is a region that acts like a fluid on geologic times. It's still rock, but over very millions of years, it actually flows. And there is a slow convection in the asthenosphere, and the lithosphere plates float atop this plastic region. At the bottom of the upper mantle is what they call the transition region. This is maybe the source of the basaltic magmas. This is where materials that have peeled off from the crust and dropped down become heated enough that they regain their buoyancy and again start their rise back up to the surface. The lower mantle is solid, contains the higher density materials that form under really high pressure. About half the mass of the Earth is in the lower mantle. Below that, we have the core. This is mostly iron with a little bit of nickel. It contains about 1/3 of the mass of Earth. It was probably all liquid at one point, but the interior of the Earth has cooled enough that there is an inner core which is solid. Earth's interior structure, crust, mantle, core, serves as a template for understanding the other rocky planets. If we look at Venus, Venus is expected to have a similar interior structure to Earth. The major difference is that Venus is a one-plate planet. We're not exactly sure why. When we look at Venus, the tectonic features are spread everywhere, not like on Earth where they were aligned with plate boundaries. There are no plate boundaries on Venus. The entire surface appears to be no older than a few 100 million years. So their tectonics are expected to be compressional, sideways and up and down. Here is a view of the Aphrodite Terra on Venus. And in the center, the red pinkish regions are Obda Regio and Thetis Regio. These are called tesserae. And these are some of the oldest regions on the surface of Venus. They show this complex deformation and probably were caused by convective motions in the mantle, raising and lowering the crust. This obviously was followed by planet-wide resurfacing because over 80% of the planet is volcanic plains. So for Venus, lava flows are the most significant interior manifestation on the surface. Mercury has a very high density that indicates that it has a very large iron core. The iron core extends more than 2/3 of the radius of the planet. Originally, we believed that it would have cooled off and become solid, but recent observations have shown that at least it is partially molten. Now, Mercury shows no tectonics, but it does show an interesting feature called fault scarps. This is an image of a scarp, and what the scarp is this line working from the center down through these craters. This is a geologic fault, and features like these indicate that a region of the surface has compressed. We believe that perhaps there even was global contraction of the entire planet during its formation. It formed and it was hot, and slowly cooled and cracked as it cooled. Mars has a lower density than the other rocky planets. Earth's density is up over 5 grams per cubic centimeter. Mars is more like our moon and down around 3 grams per cubic centimeter. It likely has a lower percentage of iron in its composition, and therefore it has a correspondingly smaller core. The core of Mars only extends out to about 30% of its radius instead of 50% as we see here on Earth. The expression on its surface in Mars is most noticeable in a region called the Tharsis Bulge. In this topographic map, you can see this giant red region over here that has been uplifted several kilometers above the average radius of Mars. In the Tharsis Bulge are the giant volcanoes, including Olympus Mons, the largest volcano in the solar system. This likely indicates that in the mantle of Mars, there has been sustained regional motions that have continued to push up. We don't know why this should be, and particularly why it should last for billions of years that it obviously has in order to produce the extensive volcanism we see here. I would say that compared to Earth's plate tectonics, the other rocky planets have relatively mild expressions of their interiors in their surface features. If we look at the large moons and the minor planets, we don't see any tectonics. What we see is really a sequence from differentiated bodies down to undifferentiated bodies. We start with the moon. The moon has a relatively low density compared to Earth, about the same as Mars, and it means that it probably does not have a core. This diagram here shows a core, but considering the density, we really doubt that it has a true iron core. The moon is geologically dead. We see some ancient crustal extension and contraction, stuff that happened during its formation, but it has had no activity for the past 2.5 billion years. As for the asteroids, we would expect the small bodies of the asteroids to cool efficiently. and the heat of formation would be lost, and therefore they would not be differentiated. Unfortunately, the evidence disagrees with our expectations. We see iron meteorites. They fall to Earth, and these can only come from a differentiated body. They are pure iron from these meteorites. And they indicate the complete breakup of differentiated bodies in the asteroid belts. So some asteroids must be differentiated, and we'd expect the largest ones to be. Here's a diagram of the largest one, Ceres, and it is likely to have a differentiated interior. We have observations that show it has a difference between its crust and an icy layer below that crust. The density of Ceres requires that there be a rocky interior below that. And this diagram doesn't show an iron core, but we believe that to be present as well. Only a few other asteroids are large enough to be differentiated, and most asteroids, we believe, are undifferentiated. Moving on to the Galilean moons, the most interesting one is Europa. This image here shows what we call the ice rafts of Europa. This is a fractured surface that shows a complicated jumble of ice. In a global view, we see much longer striations, these long lines of fractures that extend across most of its surface. This image looks somewhat like what we see here on Earth at the North Pole. Now, these radial lines are just indicating where the North Pole exists, but these other lines are fractures in the ice above the Arctic Ocean. We take the same idea and apply it to Europa and deduce that there might be a subsurface ocean on Europa. So Europa's interior is differentiated, has a metallic core and a rocky interior, but out towards the edge, it has covered with ice and may have perhaps a 10-kilometer deep ocean. The evidence is consistent with this ocean only existing in the past, so we're not entirely sure that the ocean exists at present. We look at the other Galilean moons. In the upper left, we have Io. Then we have Europa in the upper right. We have Ganymede in the lower left. We have Callisto in the lower right. These are diagrams of their interiors as inferred from gravity field and magnetic field measurements. All but Callisto are believed to be differentiated. They have an iron core surrounded by rock, and all but Io have an icy surface. Io, of course, has extensive volcanism and would not have an icy surface. It is interesting to note that Ganymede and Callisto may also have subsurface oceans. The evidence for this comes from a small variability in their magnetic field. We noticed on Europa that its magnetic field varies just a little bit, perhaps due to the subsurface ocean. Now, to do this, to create a magnetic field, you need an internal conducting fluid, because electricity and magnetism are complementary. Wherever you have an electric current, you generate a magnetic field. If a magnetic field changes, you generate an electric current. So for Ganymede and Callisto, when we see changes in the magnetic field, the best explanation we can come up with is a subsurface ocean. Now, Europa and Callisto have only tiny magnetic fields. They're really not intrinsic to the body themselves. They're more a response to Jupiter's magnetic field. Ganymede, however, has a thick ocean layer and has a significant, or shall I say, it is drawn to the thick ocean layer because it has a significant internal magnetic field. Moving on to Saturn, its large moon Titan is also suspected of having subsurface ocean. It is larger than Mercury, so we expect it to be differentiated and have rock and ice interior. We also suspect that it has a water and ammonia liquid layer about 50 kilometers below its icy surface. At the very outer edge of the solar system, Neptune has a large moon, Triton. Triton is thought to be undifferentiated mix of ice and rock. This is due to its gentler formation in a cold region of the solar system. I also note that ices can stick together under gentle collisions and don't need to heat up that much. Pluto is very similar to Triton in most properties, but it's just a little smaller. So we would expect basically the same interior for Pluto. Finally, we turn to the giant planets. The interiors for these are mostly determined by modeling. and we find that Jupiter and Saturn are different from Uranus and Neptune. Jupiter and Saturn are composed roughly of solar composition of hydrogen and helium, 75% hydrogen, 25% helium. The outer layer is gaseous molecular hydrogen. These are the atmospheres that we see. But as you go deeper and deeper into it, that gas becomes really more like a hot liquid. And at about 1 million times Earth's atmospheric pressure, the hydrogen breaks down and becomes a liquid called metallic hydrogen. In the very center below this metallic hydrogen, there's a core, and we presume it to be a mass of rock about 15 times the mass of Earth. We have no direct evidence for it, but we need to postulate this mass of rock as a nucleus for the formation of Jupiter and Saturn. Basically, you need enough mass to attract and hold the gases that form the rest of the planet. Jupiter's density indicates that it is dominated by its liquid hydrogen phase. So though we call it a gas giant, from this viewpoint, it's really more a liquid giant. And Saturn's density is actually below that of water. In fact, by volume, it's mostly gaseous hydrogen. Uranus and Neptune are significantly smaller. They form farther out in the solar system, and instead of accreting gas, because they didn't have enough mass, they instead accreted ices. The ices in this case means water, ammonia, and methane. Uranus and Neptune's interior starts with a small rocky core, perhaps a few Earth masses. Then outside that, we have a dominant component that is hot, highly compressed liquid. This is the ices and various chemical species derived from these ices. The outer 15% of these planets is molecular hydrogen gas. So Uranus and Neptune show a completely different structure from Jupiter and Saturn, and some people refer to these guys as ice giants as compared to Jupiter and Saturn as gas giants or even liquid giants. That completes our journey to the centers of the planets. Now you may notice that there's one external manifestation that we've not yet discussed. Magnetic fields are generated in the interior of most planets, but the effects are seen on the exterior. In particular, magnetic fields interact strongly with the solar wind. We will discuss magnetic fields in detail in the context of solar storms in a few lectures. In the meantime, we're going to work our way out to that region. Our next lecture will move from planetary interiors to planetary atmospheres. We'll see you then. Take care.
So I hope you enjoyed that. That's complemented sort of stuff I had. So I brought a lot together and expanded on a few items. So yeah, any questions around tectonic and volcanic forces, how heat's coming up and it changes the top? Yeah.
Why do the upwellings of magma only happen in the ocean as opposed to on the land? And why is it always basalt?
Yeah, basalt's one of the igneous rocks.
Okay.
Yeah, it's just one of the igneous rocks is basalt. And what was your first question?
Well, there are actually some places where it does happen on land, like the Rough Valley in Africa. And
Why magma only comes up in the middle of the ocean?
Right. Oh, I see. It's made predominantly that.
Why?
Oh, I think it's the oceanic crust is thinner, so it's easier to break through and push those plates apart. It's just too thick. The continental plates are too thick to break through. Yeah, good question. Yeah, Daniel.
I've got a question about gravings, because you mentioned about how it's quite popular on Mercury. And
Yes, it's unique to Mercury.
Yeah. I'm just wondering if, like on Earth, you'd be able to find like a place that you could actually see one, because
Yeah, quite if you spoke again, there's a horse up on the side, so it refers to sunken ground. And I think it's just large patches. I'm sure if you get that, it's just large patches of it. Yeah,
The simplest area of training for is officially Horston Road.
there you go.
That's the geological termination for it. So Spectari, marks through to the beginning of the mountains is officially a very ancient geological formation. And it's Horston Ground, and it goes up and it goes down.
Did you hear that, Dan?
oh yeah,
I'm not sure where else, but
Yeah, when it's that unique to Mercury, that's widespread over there. It's a recognised geological thing,
yeah,
yeah.
I think it'll be interesting to see on Earth as well.
Yeah.
So I
Go,
think,
I'm sure just go and Google it and see that Yeah, that's
Oh,
right.
yeah.
Otago,
Okay.
yeah, Tony, yeah.
A local bit of interest in terms of Continental Rift, that a couple of years ago I did a fair bit of detailed study of the movement of the local plates, and we've heard a lot about the fact that the Zeiss telescope is, got these deep legs that frame that go down into the rock of the plate. That telescope is a kilometre or two further north now than when it was installed.
Wait, what?
Because the Austro-Indian plate is one of the fastest moving plates
Yes.
on the Earth. It's moving northward and we're going with it.
Right, yes.
Yes, and the telescope's going with it.
Right.
So the Germans put it exactly where they wanted it,
Yes.
and that's where it is now, is it further north.
So how far has it moved?
Oh, I don't know the exact
Oh,
distance,
yeah.
it's hard to determine from the records.
Yes, yeah.
It's several metres.
Right, yes.
It's not a kilometre or anything, it's just several metres.
Yeah.
Not enough to affect the alignment of the.
Yeah, I was gonna say.
They do mock with GPS and
We
stuff.
talk
yeah.
about the alignment, and I had a mischievous theory that it was being rotated by the Pacific plate. It's actually not, it's still aligned.
Right, yes.
Yeah. If you measure it, it's still very much aligned.
Each of the big earthquakes moves New Zealand either closer to or further away from Australia. You don't see
Is that
it.
good or is that bad?
Fine.
No, I'm only joking.
But you
Further away.
don't see it in the Herald, but the
Yeah.
Otago Daily Times used to tell us every major earthquake. And the one we're waiting for, of course, is the Alpine fault.
Yes.
That's well overdue to go twang, and that'll probably move us, I think, something like 15 metres. I'm not sure whether it's closer to Australia or further away. Auckland will feel that.
Yeah.
There was a big one down in Tamarunui just last week, and
That's right.
it was interesting because you talk about subduction and what have you with the plates. Tamarunui itself, the people around that area, didn't really feel it that much, whereas people down Palmerston North and out in Napier on the east coast, they felt it much more strongly, and it was to do with the subduction of the plate, and also that one plate is much more rocky and
Yes.
hard, and
Yes.
the other plate is more, I think it's the Australasian plate, is more smushy and soft, so it amplifies it.
Yes, yes,
And
yes.
so you get a lot more shaking and movement, and you feel it a lot more.
Yes, yes, yeah.
Yeah.
Fascinating science.
But there's been a lot, just recently, there's been a lot of quite reasonable sized earthquakes up through out in the oceans in the last couple of months or so.
Yeah.
I watch what's going on with them.
They're all quite fun.
Yeah, some of them are, some of them aren't. But there's been a few shallow ones just in the last week or so. But they're out in the ocean, so there was a 5-foot one yesterday out of Gisborne,
Yes, yeah.
but we didn't feel it much on land.
Interesting, yeah. Peter, you have a question?
Yeah, Chris, some of the areas on Earth were originally covered with ocean. I'm thinking of some areas in Australia.
Yes.
So you would think if the crust was thinner there, why isn't that effect happening in those areas, or has it? Do you know what I mean?
What sort of effect do you refer?
Well, the upwelling that you were talking about,
Yes.
it seems to be particularly evident under the ocean, as Bill said, not always, but
Yes, yes.
quite often under the ocean. And you rationalise it by saying, well, the crust was a lot thinner
Yes,
there.
yes, yes.
So what I'm saying is where there used to be ocean,
Yes, like
is the
Everest.
crust still thinner? And if it is,
Oh, it's because it's been lifted up like Everest has just
Yeah.
been pushed up. Yeah, Everest was, it's got, as I said, it's got a sedimentary layer. It was once on the bottom of the ocean. And the plates have just been brought together. It's just pushed it up, up here, that folding, that foot of folding, where two plates converge, and they just, you might have ocean, two plates converging, and they just mountain range lifts up. Everest was the bottom of the ocean.
I was thinking of the area where you said that they pulled apart.
You see the divergence,
Yeah.
divergence in areas, yeah.
You know, places like Everest, it's sedimentary rock, so it's under the ocean, but it probably would have been on the continental shelf, so it wouldn't have been in the stuff that came up from the deep ocean. So,
And that's
yeah.
converging versus diverging.
I'm just saying about the case of the spreading occurring on land, the most common example is the Rift Valley in Africa.
Yes, you did mention that.
Yeah, and what geologists think apparently that eventually that will basically form a basin that will get invaded by the sea. So you actually end up with the land breaking apart and a new sea forming. That's basically what they think happened to with the Atlantic. Was the land masses on both sides of the Atlantic was supposedly once joined, and a rift is formed, and the ocean is actually formed in the rift. As it's gradually spread over many millions of years. There's some simulations on the internet where they sort of speed up how the continents have moved in the past and how they think they will happen in the future. So,
Any other questions or comments? To yeah.
Chris, there's a contradiction tonight. You mentioned that there was seismic activity measured on the moon,
Yes.
and the professor in the movie said that it was geologically dead and there
Yes.
had been nothing activity
Yes.
for 3.5 billion years or something.
Correct. Yep. That's not correct. The moon is geologically dead in terms of there's no real big heat process of heat being driven up. The astronauts put their probes down, heat sensory probes down to inject on that. But as the guy in the first little movie clip comments on, most of the moonquakes are from tidal forces. Just the moon is being stretched as it goes around the Earth. It's just the stretching and pulling, as opposed to geological activity going up underneath it. So that was what they're referring to. It's dead geologically in terms of hot molten and stuff, but it still gets, because it's in synchronous rotation on the Earth, as it twists, it keeps the same face facing us. So it's getting pulled and stretched with those tidal forces, and that's what's doing it. Yeah. And he mentioned the odd meteorite. And just out of interest too, to calibrate their instruments, and there's twofold. But the Apollo astronauts, when the lunar modules went up in their ascent stage, they went back into the command modules. They then purposely sent their ascent stages they came up in around the moon a few times for the purposes of to see how long it could actually survive. And that piece of information came in very, very handy for Apollo 13. They knew they had a lifeboat on board with the ascent stage. So they experimented with that, but when they finished doing that, they purposely crashed it into the moon so they could measure it with their seismic waves. Why wait, a year or two for an actual one when you can create one yourself? So just a little bit of trivia there. So to answer your question, it's tidal forces that are doing it versus geologically active things. Yeah, good question. Yeah. Anything else? Otherwise, we're all good. Sounds like someone's having some golf walks outside. So next month is John Wishart's going to be talking for 30 minutes on just how the media portray astronomy news, and so something will come up scientifically and how the media starts to portray it, and so that's an interesting topic. And the second half will be the annual quiz, so that's always a lot of fun. So see you then. Right on.